Okay, let's start. The warm-up problem is that I give you this very simple matrix. A is 1, 1, 1, 1, 1. It's a 5 by 2 matrix, and ask you to find U and V. One is a vector of size 5, the other is a size 2, such that A equals to UV transpose. Give you a minute to think. Okay, so let's work on this problem. So this one, I don't know how to deal with it, but since the matrix is so simple, I can try to see whether I can come up with a solution directly. So first of all, the columns space is clearly spanned by 1, 1, 1, 1. Let me just try. The row space is spanned by 1, 1. Okay, so let me try this, whether it works. So then UV transpose. So this is 1, 1, 1, 1, 1, 1, 1. And you just multiply and you find this is exactly A. Okay, so it's a really simple problem. So what do we learn from this? First of all, let's see, I can generalize the principle to any M by N matrix. So A is an M by N matrix. So if there exists U in Rm and V in Rn, such that A is equal to UV transpose, then A is a rank 1 matrix. Here the rank is exactly the same thing as we have learned in chapter 1, the rank of the matrix, which is the dimension of the column space, because you can see all the columns are given by some number times U. So now let's look at the cost. If I want to store this matrix A on the computer, say, so the storage cost of A is, I need to store the n numbers. So this m times n. But equivalently, if I don't insist on multiplying this u and v transpose, we're satisfied by keeping A to be of this form, because obviously this is all you need to do, let's say, a matrix vector multiplication. Give me another x in Rn. Ax is just a u v transpose x, the inner product between v and x. So really, this contains enough information. We don't need to necessarily store A explicitly. Then this is just a m plus n. When m and n are large, you can see that m times n is way larger than m plus n, and therefore this is much reduced storage cost. The generalization of this simple example is really the topic today, which is called singular value decomposition, or SVD. So the story of SVD was that in the 60s, I mean, it remained to be some concept that is mainly used to construct some proofs and other things. But it's gradually, in the past few decades, have found so many different applications. Really, almost all sorts of fields you would see this. So at the beginning, even a few years ago, I think in the Math 54 class, we don't even talk about SVD, but now it is so important. So we added this to the book, and so we're going to talk about that. This is book chapter 7.4. So naturally, we would like to compare singular value decomposition, which is to be introduced, with a thing we have already learned, that is the eigenvalue decomposition. So eigenvalue decomposition, especially we just learned on Monday for real symmetric matrices. But generally, we need to work with n by n square matrices. Eigenvalue decomposition is directly related to diagonalization, or a decomposition of the form AV equals to VD, or V invertible, and D is a diagonal matrix. And what it means is AVI equals to lambda IVI. In other words, in the real O complex, along the real O complex axis, we have a vector, so this is VI. Then A acting on this vector is not some very complicated operation that changes both the length and the direction of the vector, but actually it is just a scaling operation, a multiplication operation of the same vector. So it's only scalar multiplication, but along the direction VI. So obviously there are two drawbacks. One is that even A is a square matrix, it may not be diagonalizable. For example, 0, 1, 0, 0, and this is not a diagonalizable matrix. Two is that if A is not a square matrix, this is useless. Why? Because if A is n by n matrix, it maps a vector from Rn to Rm. Therefore, it's impossible to have AV to be a scalar times V. They're not even in the same vector space. Today, the singular value decomposition overcomes the problems above. It is applicable to any matrix. Any matrix. There's no exception. So to get you some idea about the singular value decomposition, let us look at an example. Okay. So this is a Julia code with our the class mascot, our duck. So you don't need to really run this code, but if you do want to do so, this one means you need to install some packages for the images and image value K. then use these packages, I load this image. You can see this, right?
Yes.
Okay, yeah. So what I want to do is to convert this into a matrix. So what is a colored image? It really has, at least, I mean, it depends on the representation. It's not really a matrix. There's the red, green, blue channels. So it's at each point is a vector. That's not good. Let me convert that to a grayscale, say. So it is really just showing how bright this point is. It can be characterized by a number from 0 to 55, or from 0 to 1, however you scale it. Then I convert this to a matrix. So it plots out. This matrix has 247 rows, 230 columns, and I just multiply them, and this is the storage cost. It's very intuitive, right? Now, what I want to do is to see whether I can find a compressed representation of this thing. This is the magic line we're going to discuss today. It is called a singular value decomposition, SVD. It has 3 components. I do SVD A. It returns a unitary, some U is actually unitary, a diagonal matrix called S, and another matrix V is actually also unitary or orthogonal. Then I just to let you show that A equals to USV prime means transpose, actually means complex conjugation and transpose, the star operation we talked about last time. But USV, they are real matrices, so this is just a transpose. What I'm showing you is the difference between A and USV transpose. This double bar means some norm, you don't need to worry about that. Just says the error is really small, and therefore A is numerically equal to U times a diagonal matrix times V transpose. If you compare with the eigenvalue decomposition, A equals to V times diagonal of D times V transpose. If A is real symmetric, you find this is really similar. But this is a rectangular matrix, right? What I'm showing you now is now I have this singular value decomposition. How should I use that? What I want to do is I do a so-called low rank compression. Sounds like a fancy name, but it is really, really simple. It says, I just take the first, however, rank of U. Now, let's say rank equals to 1. I just take the first column of U. I take the first entry of S, and I take the first column of V and transpose that. I obtain a matrix called A compress. If rank equals to 1, then the cost of storing that is really just M plus N. But I can take 2 columns of U, 2 numbers from the diagonal matrix S, 2 columns of V, and so on and so forth. Is that clear? So then I print out the storage cost, which is this, the number of rows plus number of columns times the rank. And then I display the corresponding picture. Remember, the original picture looks like this. If I do a rank 1 compression, it's just a blob of things. You can even see this textures, okay? So this thing here. So this is really that, remember, this is just a rank 1 matrix. No matter whether you look at along the rows, along the columns, so it's only rank 1. So just to see, roughly, there's a blob of things here, right? I mean, the total cost, storage cost was 50K. Now I only used 400 numbers, just to see a blob of things. Now I gradually increase the rank. rank equal to 5. So the storage cost now becomes 2,000. And you can see some important features have been automatically extracted. Remember, I only had one line of code just to do the single value decomposition. So there's some features, they're here, but by eyeball norm, obviously, this is not a very good compression. Now we're all kind of stuck at home, and if you watch Netflix, the quality of the video is like this, you won't be very happy. Now let's do a rank 10 compression thing. So now you can see this is dramatically better, but still you can see all these textures because in the end, this is just a rank 10 matrix, right? So we do a Gauss elimination and convert that to the row echelon form. There are just 10 pivots here, and that's it. But this picture is already much better. Rank 20, other than a few ripples, you can still see these kind of things here. You almost have exactly the same picture. So now things start to become acceptable. Rank 30, and all the fine features are out. I only used the 30 columns, but you can imagine that, I mean, there's really not that much difference between this column and this column. The fine-scaled features are a lot more difficult to extract. And finally, at the rank 40, this is essentially the same thing as the original matrix. So this is what we're going to talk about today, which is how do you construct singular value decomposition for a general matrix, and how do you actually do this low rank compression. Any question? Okay, so let's start the journey. It's actually not complicated at all. So we have to overcome a problem that is A is n by n matrix without loss of generality, WLOG, without loss of generality. We assume m is larger than n or larger than or equal to n. Otherwise, just consider A transpose. This is really just for simplicity. So we don't have that many tools to talk about rectangular matrices other than Gauss elimination that we had learned at the very beginning of this semester. But we learned eigenvalue decomposition. In particular, we learned that any real symmetric matrices is diagonalizable. So how do we get a real symmetric matrix? The trick is to consider A transpose A, which is a matrix of size n by n. Furthermore, this is real symmetric. So we can do spectral theorem, spectral decomposition theorem. Let's do that. So it's guaranteed that there exists an orthogonal matrix V equal to V times D. Okay, so we have V transpose V is eigenvalue times n. D is a diagonal matrix. But you see, A, so this one, all the eigenvalues, in fact, all the eigenvalues of A are non-negative. A transpose A are non-negative. So, this is sigma 1 squared, sigma n squared. So what do we have? So we have A transpose A this one we did eigenvalue decomposition, and this is a non-negative matrix. For simplicity, let's also define sigma to be formally d to the 1/2, which is just this matrix, sigma 1, sigma n, and I can choose sigma I to be non-negative. Because this is square, I can always choose the positive square root. Okay, so this is the first step. The second step is to to define a u. The procedure looks a little bit magical at the beginning, but we're going to explain further. I define u to be the following matrix, to be A times V times sigma inverse. Here, for simplicity, I first assume all sigmas i's are bigger than 0, so that the sigma inverse can be defined. So why do I want to define this matrix? This is because using this and V is actually orthogonal. We immediately have A equals to U. Sigma V, the inverse of V, is V transpose. V transpose. Therefore, we have, this is the SVD we look for. So, what's the features of this singular value decomposition? So we said A, V transpose V is IN. So this is where V is an n by n orthogonal matrix. B, sigma is sigma 1 sigma n, and each one is non-negative. When there's a 0, we need to do something else. For simplicity, I'm not discussing that. C is this U is also an orthogonal matrix, which is an m by m orthogonal matrix. So this means I have an m by n matrix. This is equal to, I have, this one has orthogonal columns. Sorry. Has orthogonal columns. So this one is m by n. Originally, this means I have a full dense matrix times n by n, which is this sigma, and then times this n by n matrix, that is V transpose. Any question? Okay, now let me show why C holds. This is a straightforward calculation. That is, remember what's the definition of U? It is AV sigma inverse. So I compute U transpose U. This is sigma inverse. The transpose of the diagonal matrix is itself. V transpose, A transpose A. And this is V sigma inverse. Recall that A transpose A, this one has eigenvalue decomposition. This is V sigma square V transpose V sigma inverse. Now I use, this is a orthogonal matrix. This is orthogonal matrix. Becomes identity. Sigma inverse. Sigma square. Sigma inverse. Exactly cancel. In. So indeed, the C holds, assuming that all the sigma i's are positive. Any question?
Yes. Why is it that our sigma squared matrix is defined as all positive?
Is defined as all positive?
Rather,
So
why is that the result?
it's because the sigmas are chosen to be all positive. Or not, so you can always choose the sigmas to be non-negative. For simplicity, I'm not talking about the case where some of the sigma i's are 0. I'm going to talk about that later. But if you assume all the sigma i's are positive, then the sigma inverse would exist, and we can find U transpose U is IN.
But why is the diagonal matrix with the sigma squared values, why are those all positive?
Okay. So the question is that why this D matrix? So these are all positive. So this is that the question? Okay. Yeah. So this one we have to take as a fact for now. That's a good question. So let me explain this fact a little bit. So the question is why D sigma 1 square sigma n square, and this is actually a little bit related to something we didn't talk about called the quadratic form. So let's compute this let's see, there's a matrix A transpose A, and I for any x in Rn, I can consider this. This is very similar to the last problem we talked about last time. That is we define inner product, and remember, in order to define inner product, this must be a positive definite matrix. So this one, you see, is A x transpose AX, and this is the inner product of AX with itself. So this one is guaranteed to be non-negative. Then there is a result. Let's say take this as a fact. So if a matrix A satisfies this property, and then all the eigenvalues of A, so fact is this. If I consider, let's say, a matrix B, which is n by n, symmetric, A transpose A is obviously symmetric, X transpose B, X is non-negative, then all the eigenvalues of B will be non-negative. So for I goes 1 to n. The reason is you take just to take x to be the corresponding eigenvector, and we have this lambda I. This lambda IB is just a transpose B, BI, and therefore it's non-negative. Is that clear? Did I answer your question?
Yes, thank you.
Okay. Any other question? Okay, so we have now shown that there's A equals to U sigma U transpose. So similarly, there's a very symmetric construction, which is V sigma U transpose. I have a V sigma U transpose, and where this is an n by n matrix. So this is equal to n by n times n by n, but it's a diagonal, times n by m matrix. So how does it compare with eigenvalue decomposition? Recall that eigenvalue decomposition says AVI equals to lambda I BI. Now, for A, which is m by n, as I said, this is not possible, but I can consider the matrix U consisting of n columns, I talked about there, V consisting of all the columns here. Then I go from, I have AV equals to U sigma. In other words, I have AVI. I don't know what that is, but it is actually sigma I, a number, times the vector UI. You say, wait a minute, so this doesn't make any sense. I mean, I can just define UI to be the result of AVI. I mean, give me any vector VI, I mean, there's always some AVI, but not really. These U's are orthogonal to each other, which is really the non-trivial condition. Similarly, as I said, there is from this one, we have A transpose U equals to V sigma. A transpose U equals to V sigma. And what this one means, column by column, is A transpose UI equals to sigma I VI. So these two equations gives really the geometrically what it does, which is I go from a space. This is Rn. This is Rm. Going from here to here, it is we use the matrix A, so it maps a vector V to another vector U, but scaled by sigma. Similarly, if I consider from Rm to Rn, we use A transpose. It maps a vector U to this V sigma. And so the eigenvalue decomposition, as you can see, if A is a real symmetric matrices and this is real, I go from Rn to Rn, then the single value decomposition in this particular case it coincides with the eigenvalue decomposition. Any other question? Any question? Let me talk about the compression. So how do I use singular value decomposition to achieve the reduced storage I talked about earlier. So this A equals to U sigma V transpose can also be written as U1 N sigma 1 sigma N. This is V1 transpose Vn transpose. This is just a summation. Let's see, I Ui sigma I Vi transpose from 1 to n, right? Okay, so in many cases, the sigma i's, they're not all of them are very big. The sigma I can be very small, smaller than a number, let's say epsilon, for all I that is bigger than k. I can how do I do that? I order sigma 1, sigma 2, sigma n in a non-increasing order. Then there is going to be some threshold so that the sigmas, and many of them, they're really small. So that means I can define AK to be sum 1 to k. I only keep those singular values and the singular vectors that are actually important. So this means this is a so-called rank K compression. As you have seen in the example I showed earlier, this compression can be pretty good, even for image with 200 or so columns. And using 40 or so columns, the result already looks indistinguishable from the original one by eyeball norm. In fact, there is a more general theorem, which in the informal setting, it says that A minus AK is indeed very small. Actually, this is, in fact, this one from the SVD can be the best by some norm, the best approximate rank K approximation to R to A. I didn't plot out the singular values in the example earlier, but it's a kind of awkward for me to use the mouse to show you. I will upload the notebook, the Julia notebook, to the website with the singular values plotted out, and you will be able to see more clearly how the singular values decays for that matrix. Any questions? Let us look at the example that how do we really compute the singular value decomposition. In the exam, we won't talk about really computing the SVD for 200 by 200 matrices. I wouldn't be able to do that. But let's go through the procedure. So A equal to 1, 1, 0, 0, 1, 1 for this matrix. Procedure is very mechanical. First, you compute A transpose A. So this is 1, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1. So this is 2, 1, 1, 2. This is, of course, a real symmetric matrix. I can compute the eigenvalue decomposition in the sigma squared. So this is really chapter 5. So I won't bore you with the details, and I'll just give you the answer. This is square root of 2, 1, 1, minus 1. Sigma squared is indeed a positive matrix, 3, 0, 0, 1. Any question? Step 2, compute U. Always look like this. So this is 1, 1, 0, 0, 1, 1. And this is 1 over square root of 2, 1, 1, 1, minus 1. And sigma inverse is 1 over square root of 3, 0, 0, 1. It's quite suspicious whether this is a real orthogonal matrix, but nonetheless, we can just carry out the calculation. This is let's carry out. So this equal to. So here I first have there's a 1 over square root of 6. This is 1. This is 3 over 6. And this is 0, 1 over square root of 2. So indeed, you can see each column is normalized, 1 over 6, 4 over 6, 1 over 6. And this is positive, this is negative. So indeed, we have this is equal to I2. So then we have A equal to U sigma V transpose. So this is a 3 by 2 matrix. This is a 3 by 2 matrix. It's 2 by 2. It's 2 by 2. We obtain the SVD. Any question?
Yeah, I have a question.
Yeah.
So in the textbook, when they go over this, they, for some reason, for the sigma matrix, they put a ton of zeros on the rightmost and bottommost columns, and the same for the U and V matrices. Why do they add these extra zeros?
Very good question. I'm waiting for this. Thank you for reading the textbook before the class. So the question is why this is a little bit different from that in the textbook. So this one in the literature is also in the textbook. It's called the thin SVD. The thin part refers to here. So you see, there is a little bit of asymmetry between U and V. So V is a bona fide orthogonal matrix. It's 2 by 2. U seems to be somewhat handicapped. So it has 2 orthogonal columns, but this is really U is not an orthogonal matrix. This is, it actually, it has orthogonal columns, but with missing, but with some missing columns. So how do I make U an orthogonal matrix? In this case, we want to promote a 3 by 2 matrix to a 3 by 3 matrix. The answer is very simple. U now has 2 columns, U1, U2. I can find another column called U3, make a 3 by 3 matrix, And how do I do that? I can just use Gram-Schmidt. That is, I find some random column and then orthogonalize with respect to U1, U2, and normalize the resulting column, I get U3. So now I try to have U. Let me call this U, put a U tilde here. Now I want to have U tilde sigma V transpose. This is still a 3×2 matrix. I'm not touching this. This now becomes 3×3. Then this is sigma. It also have to be modified, become a 3×2. That's the only natural conclusion, right? So we have, I need to put a tilde here, put a tilde here, I put a tilde here. I have already chosen U tilde to be this one with an additional, some random column. That's orthogonal. How do I change this is sigma? See, this one is U1, U2, U3. What I want to do is to get rid of this thing. This is sigma 1, sigma 2. This I don't want to touch. All I need to do is to add these two rows of 0 here. V1 transpose, V2 transpose. By adding this 0 and by adding this U3, you just do the calculation and you will find that this is still U1 transpose sigma 1, U1 plus U2 sigma 2. Sorry, U1 transpose, and this is V2 transpose. The result doesn't change at all. So instead of the thin SVD, you can say either a full form, or let's call it full SVD, is A equal to U tilde sigma tilde V transpose. Again, I assume M is bigger than N. This is M larger than N. This is M by N. So this is M by M. This is M by N. And this is N by N. But because you do exactly the same procedure, you'll find that the rest of, so U tilde, that's U1, UN, but N plus 1. These columns are not useful, so sigma tilde takes the form. This is sigma, and this is just a 0. This is M, this is N, N. The rest of the M minus N rows are 0. Did I answer your question?
Yes, it did. But I'm wondering, since doing the full SVD is such a much more complicated process, what are the benefits of just gaining an orthogonal matrix U tilde?
It just looks better. That's it.
Okay.
Yeah, there's no real benefit at all. In fact, as you can see, when we do the compression, we would like to throw away the sigmas that are actually close to 0. We really want to throw as many zeros as possible. So in a real world, when you use the SVD, it's almost always the thin SVD.
Okay.
That's why I didn't even bother mentioning the full SVD at the very beginning to avoid confusion.
Thank you.
Any other questions? If not, we have finished all the parts of the linear algebra. Hooray! So from Friday, we're going to go to the second half of the semester. This is only 3 weeks or so. We're going to use the book of NS and S and go to the differential equations. Bye.